Yeah, in this lecture we're going to talk about continuous distributions. Specifically, we're going to talk about the standard normal, which is the bell shape, the normal, where the mean and standard deviations are not 0 and 1. We're going to talk about the uniform distribution and the exponential distribution. But let's start with this. So remember, we talked before about discrete random variables where the values are discrete. Now we're going to talk about continuous random variables where the possible values are continuous. So if you remember, the continuous random variable arises in situations when the population or possible outcomes are continuous or quantitative. Like if you're looking at the lifetime of a light bulb, you say it's usually x, where x between 0 and infinity, so it's very large, right? The variables of interest would not be, you would be interested in the light bulb lasting 200 hours, 35 minutes and 52 seconds. So you just say less or equal or greater or equal or between two values. So I would be interested in the light bulb lasting more 1,000 hours, between 1,000 and 2,000 hours, and so on. But for the light bulb to last exactly one possible value would be extremely unimportant. So the relevant question here is to find probabilities of events like these. They are all compound events, basically. So if you have a continuous probability density function, then we call it, then the area under the curve would be 1. So here is I'm going to start with the normal distribution, and in this case we're going to talk about the normal, the shape, and how do we find areas under the normal curve. Right? I'm going to start with the standard normal. Standard normal, it's a bell curve where the mean is at 0 and the standard deviation is at 1. And it has, we're going to use the letter Z because the Z is so popular, it's called the Z distribution. So that stands here for the probability density function of Z, or basically the shape, the distribution of Z. And it has this nice formula. It's actually, the formula is nice, but it's not easy to work with. So we're not going to use it. It's just there for you to see what kind of formula people use for the standard normal distribution. And if you take this formula and graph it on your graphing calculator or on a computer, you're going to get this shape. This is a bell shape. We've seen it before. And the area under the curve is 1. The mean is at 0. The standard deviation at 1. And that means really, if you look at this shape, it looks concave downward here. It looks concave upward here. So that means there's a point here where it changes concavity from downward to upward. And some of you may recall that as called the point of inflection. If you drop that line there, that's 1 standard deviation. Okay. And also you may recall that within 1 standard deviation we have 68% of the probability, 95 within 2, and almost all within 3 standard deviations. Although these lines extend all the way to infinity and stay above 0, but they're very, very close to 0. Okay. So what we are interested in here is to calculate areas under this bell curve, bell shape, but not just at 0, 1, and 2, but also at fractional points like 1.33. So the tabulate, we're going to talk about how these values are tabulated, but before that, if I ask you what's the area between 0 and anything to the right, that's going to be half of it. So this curve is symmetric at 0, so that's 0.5 here and 0.5 down there. And because of this symmetry, I don't need to tabulate all the probabilities for this curve. I can tabulate probabilities between 0 and points to the right, and by symmetry I can compute the probabilities of similar points to the left. Okay, so that makes things easier. At least that's what your textbook does. So we're going to compute probabilities of this form. Z is between 0 and a small little z to the right. Means z between 0 and this point, and this will be the area. And these are the areas. So all these probabilities are tabulated. So this shaded area here is the one that's tabulated here for each value of z. So if z is 0, that area would be 0 here. And as I shift z to the right, those numbers grow until z goes all the way to this is part of the table. After I get at 3 points, it would be 0.5. So this is a small portion of that table. Okay. So how do I know what that means? So if I want to find the area between 0 and, let's see what we have here, 1.33. So I want to find this area between 0 and 1.33 here. The way I would do, I would start with I go down this line, and that's 1.3. So my answer is going to be somewhere in this row, 1.3, but I have 1.33, and that's what this row here is. It represents the second decimal. So all my values have to be rounded to 2 decimals. If there's no second decimal, it would be 0. If there's a second one, and then I have to use that. So I have 1.3, and my second decimal is 3. So I go down there and here, and that point there, 0.4082, is the area between 0 and 1.33. Okay, so that's exactly what it is, and that's why we have here 1.3. That's 03, and that's my second decimal. That's my probability. And all other areas can be calculated from these ones by symmetry. And also conversely, if I have the area up in the upper tail, then I can find this area and find the corresponding z value. Okay? And that's what we call here the critical value, and I'll give you examples of that as well. Okay, so this would be the area in the tail, and this would be the corresponding z alpha. First example, we're going to say show that the probability between z equals 0 and 1 is 0.3413. Oh, we knew that. That's about 34% from our empirical rule, but let's do that. So we go to the area between 0 and the point to the right is going to be 1.00 because I need 2 decimal places, and I just go down and read it from the table. So I'm going to be referring back to this table quite often now. So between 0 and 1, I just go 1.0, and my second decimal is 0. And here is my answer here, okay, 0.3413. So that's how I read this table, this probability. However, if I want the area between -1 and 1, well, I'm going to use the symmetry property, because now I have the area between 0 and 1.34, and between 0 and -1, by symmetry is going to be 0.3413 again. So I just double my area, and it would be 0.6826. So I only need the table to get part of it and use my symmetry property to get the rest of the probability. Okay. Also, let's see, how would I find the probability between -2 and 2? I want to show that to be 0.9544. That's going to be similar, and I just basically go to, I'll get the probability between 0 and 2 and double it, and the probability between 0 and 2, so I'm going to go, I don't have, so I have to go all the way down to 2 here, 2.0, and my second decimal would be 0, and that's going to give me 4.7 something, but it's outside my piece of the table here, and double that. Same thing for -3 and 3. So if you look at these probabilities here, 68% approximately, 95%, 99.74%, these are the probabilities we got for the empirical rule or percentages. And now they are more accurate since we are using the full distribution. Okay, find z0 such that p of z greater than z0 is 0.1, and the answer is z0 is 1.28. I want to show you that. Do I have a graph for this? Yeah. So it's going to be 0.10 is the area in the upper tail here, and I want to find this value here. So I don't have that. What I have tabulated is this. So I take 0.5, this whole area, half of this curve is 0.5 minus 0.10, that's 0.4. And then I want to look at 0.4 in the table. Let's go back to the table. 0.4, I have here 0.3977, 0.4015. I don't have 0.4, but this would be the closest value to 0.4. So I mark this, and I want to find the corresponding point now on the line. So I go to 1.2. On my second decimal is 8. So the answer is 1.28. Okay, so that's what this point would be, 1.28. If I told you I want the area in the lower tail to be 10%, then the answer here, 10%, and the answer would be negative 1.28, okay, by symmetry. So we're using the symmetry property. And similar to that, we have this one here. If I want the area in the upper tail to be 0.05, that means this area would be 0.45, but 0.45 is not in the table. If you look at the table, you're going to find these two values, and if you look at these two values, they are equally distanced from 0.05. So I find the z sub 0.05 that corresponds to this one. I get 1.64, this one 1.65. So some people say, well, that should be 1.64, others say it should be 1.65, and other people just say, let's take the middle one, which is 1.645. So either one is fine, but the most commonly used value is this, 1.645, averaging these two values. Okay. Because if you have 2.5% of the probability in the upper tail, the corresponding z0 would be 1.96. This is again another popular value that's used, and use the same idea. So I want you to really verify all these examples by going back to the table, make sure you understand the table. Now once you do that, now we probably I want to pause here, do all the homework problems on the standard normal table, and now we go back to the normal distribution. Now we have a normal distribution where the mean and standard deviation can be anything. It would have this shape. That's the mean, that's the standard deviation shows here, and it's a difficult formula to work with, so we're not going to use that formula. Instead, we're going to take any normal distribution and standardize it, refer it back to the standard, the one we just worked with, and work with it from there. So in this case, the mean is mu, the variance sigma squared, the standard deviation is sigma. So this is a symmetric distribution with its mean, median, and mode are equal. It's bell curve, is symmetric around the mean. The area under the curve is equal to 1. The lines never touch, these lines of the curve never touch this line, the horizontal line, but they get closer and closer to it. Okay. So how do we standardize this? So if I have a value here on this line, and I want to find the area under the curve between that value and the mean, That's hard. So what I do is I take that value, subtract its mean, divide by the standard deviation, simply x minus mu over sigma, and that should give me the z, the standard normal distribution. And that's the idea of standardizing the normal curve, because what that means is basically taking this distribution, taking x, subtracting the mean, shifting the mean from mu to 0, and dividing by sigma means making that standard deviation equal to 1. So either squeezing it or flattening the distribution a little bit to make the perfect bell shape here. Another one I want you to look at, if you look at this formula, if you cross multiply here, you can rewrite this as z sigma equal x minus mu, or x equal mu plus z sigma, which is this one here. So I can rewrite it this way, which is fine. Okay. So here are the steps in finding an area under the normal curve. Convert each x into the corresponding z using the z-score formula. Graph the resulting standard normal area, and then use the z table to compute the required area. So here is an example. Say let x represent the intelligent quotient IQ of a randomly selected individual. If x is a normal random variable with mean 100 and standard deviation 16, what percentage of people will have IQs between 115 and 140? So we can rewrite this problem as probability of x between 115 and 140. Now we're going to follow these steps to first find the z-score of 115 and 140. So 115 minus mu over sigma gives me z1, and I substitute mu 100, sigma 16, I get 0.94. z2, I want to find the z-score of this, so that's 140 minus mu over sigma, 140 minus 100 over 16. Got z2 is 0.25, and of course the z of x is z. So now the problem is to find p of z between 94 and 250, but that's a standard problem. We've done it in the previous section. So in the standard normal table, I want to find this area now. And how do I do that? Oh, okay, but I can look in my z table and find the area between the mean and 2.5, which is the mean is 0 for the standard normal, and that would be 0.4938. So please pause and find that area in the table, in the standard table. So by going to 2.5 and your second decimal is 0, and then you want to find out the area between 0 and 0.95. So you're going to go to 0.9 and your second decimal is 0.4, and that should give you the area 0.3264. So if I look at this now, this shaded area is this bigger area, which I called A1, minus this small area, which I called A2. So I subtract them, and that gives me 0.1674. So what that means in the context of my problem is that 16.74% of the people will have IQs between 115 and 140. Or if I were to pick a person at random, the chances that their IQ will be between 115 and 140 is 0.16. Okay. Another example, quick. So if x is a normal random variable, say with parameters, the mean is mu, the variance is 9, find the probability x between 2 and 5. Well, I have to remember now I need to use the standard deviation, so I'm going to change that to sigma equal 3, and then p of x between 2 and 5, I need to convert this to find the z of 2, which would be, using the same formula I had above, would be -33, the z-score of 5.67. So again, converting those values to z-scores, and then graphing this, and computing it using the table. Let me probably show you this first one. Let's graph this first one. So we're looking for P of x between 2 and 5. So here we're looking at P of x between 2 and 5, and we said this is going to be equal to P. We found the z-score of 2, which is negative, is it 0.33 less than z, and less or equal 0.67. Let me just go back and check. No, yeah, 0.67, correct. And so second step, and again we found those from the z-scores. Second step, we graph this. So it is a bell shape. That's my 0. That's my negative 0.33, and this is my negative 0.67. So now I want to find basically this area. So first I find this area from the table. So I go to the table, and by symmetry I look under 0.3, and I want my second decimal to be 3, and this would be the answer for this shaded area. And then I want to find this area. So now I go to the table again, and I want to look at what, 0.6. My second decimal is 0.07, and then my area would be here, and that would be this area. Now I want to find the total area. So by looking at the graph, I know I'm going to have to add this and this, because this is negative here. Okay, so I add them up, and that should give me the answer, which is 0.3779. So maybe you want to pause, do this, and then try to do the other two. And these examples here, they're all the same. And next we'll talk about the normal approximation to the binomial distribution, but that's for another lecture. Thank you.